based at the Harvard campus. I'm with UCL Mechanical Engineering. And yeah, today I've hijacked this session to really talk about in situ imaging and hot cracking, but there's gas and powder interactions involved, which I will get into. Okay, so I'll just give a little bit of background about views into powders and the susceptibility of nickel-based superalloys to hot cracking, the scientific challenges and some of the prior work that has informed my studies, the methods I've used, current results, key findings, and a little bit about future work. So I'm sure everyone here is familiar with the benefits of AM technologies, but the one I'd like to focus on for the moment is the low waste compared to conventional manufacturing processes. In theory, we can take the powder that's left over after we build our parts and put it back into the machine at a later date, reducing the amount of waste overall. But as I'm sure everyone's aware, it's not as simple as just taking any powder and putting it back into your machine. In storage, the powder can pick up oxygen, and as I've just found out, that can happen during the process as well from the previous speaker. And this has a detrimental effect on the defects that can form in this process. The application of interest that I'm looking at here is turbine blades for commercial jet engines. These components are made using nickel superalloys with the amazing properties that everyone is aware of. But they have a susceptibility to hot cracking, which is only made worse by the addition of oxidized powder. So nickel-based superalloys are susceptible to hot cracking because of their large solidification range. To get these amazing properties, we have to introduce some low melting point phases, and this can introduce a problem in the process, such as laser powder bed fusion. These parts are safety critical to the engine and can't really afford to have these sort of defects present, so strategies to eliminate them, or at least better understand them, are currently needed. This is difficult to do because of the rapid nature of the process, but as I'll go on to show, using in situ synchrotron imaging, we can get an idea of what's going on inside an industrial machine. Prior studies have shown that for laser powder bed fusion, using heavily oxidized powder drastically increases the defect volume fraction in our builds. So understanding this as another process input is important as well. The aim of my PhD project is to determine or narrow down the dominant mechanism for hot cracking, which would be solidification, ligation, or ductility dip, based on prior literature. And also to investigate whether there's a tolerance for how much oxygen we can allow into our process before the defects start getting out of hand. So to do this study, I used 4 different CM247 powders, 1 virgin and 3 with high oxidation levels. These were manufactured using a heat treatment in oxygen atmosphere for varying levels of time to control the oxidation level. Here I've shown the particle size distribution, just to show that this heat treatment didn't drastically alter the size or the aspect ratio of these powder particles. And once these powders were produced, we measured the oxygen weight percent using inert gas fusion infrared absorptiometry. Here I'm showing the parameter space for this study. I started off with quite a wide parameter space with the virgin powder, and by looking at the extremes of this processing window, I was able to identify which builds are more dominated by other features like balling or lack of fusion, And so as we move to the oxidized powders, I could reduce the amount of experiments to focus really on the hot cracking problem. To do these experiments, I used a laser powder bed fusion process replicator developed by my group, and this rig is designed to be placed on a synchrotron beamline for high-speed X-ray radiography. So we have a very small build chamber here with the laser above and an X-ray transparent window for the X-ray beam to penetrate through. This is our sort of sample setup. We have a substrate with a miniature powder bed on top, constrained by 2 X-ray transparent windows. And after the X-ray passes through our sample, it's captured by an imaging setup. To get a better idea of what's going on, have a look inside the chamber. So here we have a gravity-fed hopper that passes over the powder bed, the substrate depositing our powder bed. Then when our laser is fired, the X-ray beam is triggered synchronously, so we can capture the laser matter interaction, the evolution of any features left behind or in our melt pool, and then the solidification shrinkage once the laser turns off. So I'm going to start here by showing a virgin powder build. This is the first layer that we built, and we're actually building on top of a laser powder bed fusion produced substrate here. So we could consider this as layer N+1. We see the powder bed has already been deposited and the laser scans from left to right. Sure, we have pretty good wetting of our melt pool. I think this video will loop, so you'll see that again. And then as the laser scans across the powder bed, powders entrained into the melt pool, fused to the substrate. We do see some signs of boring here, but the main feature we're interested in is in this crack that appears at the very end here. As we watch this again, we can see the powder being entrained, some spatter, but not too much. Seems like there's too much of an issue with porosity, at least at the resolution that we're looking at. And then after the laser turns off, we see the remaining melt shrink, and this crack starts to form from the top surface going down into the substrate. So from this, we already can get an idea of the growth rate of these defects, the width, where they occur within the build, and most crucially how they evolve in a multi-layer build. So let's fast forward to layer 10 of this build. We have the first crack we saw introduced in the prior video, but 2 other cracks have also been formed along the way. C1 and C3 here are very close to the substrate at the ends of the track. C1 seems to have stopped growing, and in this layer it doesn't seem to grow at all, perhaps because it's interacting with a lacquer fusion defect along here. C3 is a little bit larger, there doesn't seem to be any lacquer fusion on this side, but as you can see in this layer 10, it's not growing at all. The main feature of interest here is crack number 2. This was introduced in layer number 7 and is propagated to the top surface in the middle of the track. As the laser fires and scans over, you can see it come into contact with the molten pool. There is partial remelting of the defect, as well as some liquid filling into the remaining channel the cracks left behind. When the layer is complete, there's very little signs of this defect remaining, seemingly it's been healed, but with further processing, this defect could potentially start growing again, although cracks 1 and 3 seem to suggest that it will terminate in terms of growth. Now, if we look at the oxidized powder builds, jump straight to layer 10 here, you can see again 2 defects. One in the end of the track close to the substrate, quite similar to what we saw in the virgin powder case, but the main difference here is this large defect in the center of the track. This one is in a location of pronounced sort of waviness of the melt track. And you can see that it goes pretty much from the top surface all the way down to the substrate, suggesting that surface waviness has a role to play in how these defects evolve. The main thing I want to point out though is that as the melt pool passes over this defect, we get only partial remelting again, not the whole feature being remelted, and the liquid feeding in this case is not sufficient to fill in the whole of the crack. As we'll find out in the next slide, the size of this defect is related to the oxygenated powder. Let's go have a look at that. So we used a machine learning image segmentation technique to measure the length of the crack over all layers processed. And here we can see that this crack number 5 in the oxygenated build has actually been introduced pretty much in layer 7. There's some sort of trace of it in prior layers, but this technique is still being refined. So we'll take this peak here as our short sign that the crack is developed. What we can see here is that even though the crack has been produced, has occurred in layer 7, it's penetrated all the way down to the substrate. So what we saw in the virgin powder case, with the crack introduced in layer 7, is one that keeps propagating towards the surface as additional layers are fused on top. But in the case of the oxygenated build, it penetrates both up to the surface and down into prior layers, resulting in a much more detrimental defect. I also did some spectron tomography of these samples. Here I'm showing both of the builds we saw in situ. As we can see, that crack in the center of the virgin powder build has been pretty much completely healed and doesn't seem to be much sign of it in the 3D scan. Whereas, again, we can see that this defect in the oxygenated case is far more severe. It also has a great surface area and aspect ratio, as well as length compared to in the virgin powder case. Actually, another feature to point out between the two builds is that waviness of the melt track that I pointed out. Seems to be that with the addition of the oxygen into the process, the wettability of the melt is far worse, and we get these large amplitude waves here compared to what we see from the virgin powder case with the same laser power and scan speed. So, as well as introducing these harsher, as well as sort of making the alloy more susceptible to these defects, the actual morphology that the track takes has a knock-on effect on the defect evolution as well. So my key findings, the main takeaway is, increasing the oxygen content of your powder is going to lead to larger cracks if your alloy is hot cracking susceptible. We saw that an increase of 425% oxygen weight percent led to a crack length increase of 150%, as well as increasing the surface area. Hot cracks in the oxidized powder builds propagate into previously built layers as well as the newly fused ones, which we didn't see in the virgin case. And the increase in the oxygen concentration also caused the amplitude of the humps to increase as well. My hypothesis for why this is taking place is as follows. We know from prior studies that increasing the oxygen content in your melt pool can reverse the Marangoni flow, leading to a deeper melt pool and a larger partially melted zone. With this larger melt pool, as the melt pool is passing over our defect, the heat distribution is different than with a smaller melt pool. The area underneath the defect is being heated up, and those low melting point phases are going to lightweight. After the lightweighting, the local area is less resistant to the residual stress induced in the part, and I think this is why we see the growth in both directions. As for the humping, I think this is pretty much due to changes in the surface tension, poor wettability, essentially. And this, again, has an impact on the ability of the material to withstand that residual stress and has the knock-on effects causing the cracks to form. Going forward, I plan to apply these techniques to the rest of my data set. I have many conditions, as I showed early on, and so my strategy is to use a manual segmentation technique to train a machine learning model developed by a member of my group, and then use that to process this large data set. Haven't yet identified that tolerance for the powder oxidation. Really only looked at the virgin case and the heavily oxidized case, but as I go through the rest of the data, I hope that tolerance will make itself clear. And as for determining the dominant cracking mechanism, from what I've seen, it seems like glycation cracking is the most viable mechanism, but I'll be working with modeling teams at the University of Sheffield and my industrial collaborators to help answer that question. So all that's left is to thank those that have helped me with my research along the way, and thank you all for listening.